Well, good afternoon, everyone. My name is Charles, Communication Project Officer here at the FNQLSDI. Along with me is Francine Fallara, Geologist. Today is the third installment of our series of 12 webinars covering geology and the mining sector. Specifically today, we are going to explore rock deformation. Rock deformation?
Yep.
Rock deformation. Once again, just want to let you guys know the first installment is now available on our YouTube channel. So make sure you check that out. If you have any questions during this webinar, just type them in the chat window. We'll address them at the end of this webinar. Also, if you have any further questions down the road, make sure you send them to info@iddpnql.ca. We'll make sure to answer them as well. And finally, the next installment. So today we're concluding the first block.
Geology, yeah.
Yes, and we'll enter our second block on March 19th. So we'll cover cartography surveys. Okay, so without further ado, Francine, the floor is yours.
Thank you. So welcome to this new lesson. Okay, so let's zoom in. Participants, everything is okay here. So lesson 3, rock deformations. Done. Finishes the block 1, finishes the geological block. Rock deformation will be separated into 2, physical deformations and chemical alterations. So for physical deformations, we'll talk about the types of deformation, types of structures, and for the chemical alteration, we'll be covering the geochemical alterations and the types of alterations. So to start, what physical deformation? What causes deformation? Well, deformation, we have to understand, is changing the rock physically. So it's an action that changes the shape or distorts the shape and is explained by several types of pressure application on the rock. So the geologic term refers to changes in the Earth's lithosphere, which is related to tectonic activities, particularly folding and faulting. That's what we'll be covering today. The term lithosphere is used to describe the Earth's rigid outer layers, as we've seen in the first lesson, and it includes the brittle rocky crust and underlying upper part of the mantle. So here is a cross-section of this lithosphere and the Earth's crust. So in the middle, you have the inner core, the outer core, and what we call around the gravitational heat convection in the mantle. So the driving forces within the Earth's lithosphere will be creating these brittle forces that breaks down the rocks deformation physically. So if we zoom in, we can see the inner core, the outer core, the mantle, and what we call the outer lithosphere. So we can see the convection fluidity of the fluids here. So the hot material expands and rises, and the cooler, denser material will sink down. The circulation of material in the mantle creates forces that moves the rocks in cool and brittle lithosphere near the Earth's surface, as seen here. The motions exert great forces strong enough to rip the continents apart, but the rate of the movement, you have to remember, is very slow on an annual basis. So if we take each of these concepts, the motion is within the upper mantle, so the asthenosphere, and it's mainly responsible for deep crustal stretching, which is called extension, and compression in the overlying lithosphere. So it's like fluid-like state of rocks in the asthenosphere, which moves slowly. The brittle material is in the lithosphere and builds up after great pressure. So the stresses applied on the rocks will strain under the pressure until that point is reached where there's a rupture and it's caused rapidly. And this mainly explains and the causes of the earthquakes that propagates shock waves through the earth. The isostasy can deform rocks. So first, to understand, here is the presentation of the isostatic equilibrium in states of balance. So here we represent the continental crust, the oceanic crust, and the mantle rocks. And this is represented up here with the blocks. And when we say that we are in isostatic equilibrium, that means we are at a state of balance between the continental and oceanic crust. So this is achieved when the vertical forces upon them remain unchanged. So once we apply some changes upon either the continental or the oceanic crust, we have to understand that the continental crust is thicker and composed of less dense granitic rocks. So they float higher than thinner, denser basaltic oceanic crust beneath the world's ocean basins. That's why they are usually higher in elevation. The isostasy rebound is while part of the lithosphere is slowly covered with ice, as seen in lesson 1, it will slowly subside to new equilibrium positions. So during recent ice ages, while the great continents glaciers were formed on land, causing the crust to sink under the weight of massive and very thick ice sheets. So here is a picture illustrating the isostasy rebound. So you have to understand that the land surface rebounds upward when the ice melts. When it is covered with ice, the land goes downwards, and when the ice melts, the block comes back to a balance. The isostasy adjustments, so what we see within different types of mountain ranges is that ongoing crust readjustments to changing forces from both above and below. So the lithosphere will slowly respond and adjust to new equilibrium positions. So whatever rocks erosion strips away rocks within these mountains, these will move slowly to regain equilibrium. The final cause would be igneous activity. So heat rising from the mantle can affect rocks to expand, so causing them to lose density and rise. And the molten material from lower crust and mantle is under great pressure, so that can force its way through fractures and zones of weaknesses. Also, the igneous activity will be illustrated by a migrating magma, which displaces or deforms rocks while forcing its way toward the surface to create volcanoes. So this is shown by balloon-like magma chambers, which are deep in the subsurface. And the massive volcanic eruptions are associated with faulting. So this is often seen and associated with intense earthquake activities. The massive asteroid impacts occurring throughout Earth's history caused massive local and regional deformation too. So shattering and melting rocks from shock waves associated was caused by these impacts. Now, before going on to showing examples of rock deformations, I have to explain some basic geological principles to understand how these rocks were deformed. So the first principle is to recognize layered or stratified rocks versus non-layered, non-stratified rocks. So a layered rocks is composed of strata. Strata are layered rocks that are typically formed when an accumulation of rock material is deposited in a setting. Then as time passes over, layers accumulate on top. So a strata is the equivalent of having beds in bedded layers in our rock. One bed is called the stratum. Layered rocks are called stratified, and non-layered rocks are tagged as non-stratified. So layered rocks are either within sedimentary rocks. So best example would be the limestones, where we can see beds within the limestones, and the lava flows within the volcanic rocks. Very well illustrated within tuffs. With example would be ash deposits, or examples of commonly stratified rocks. Here is an example of a stratified rocks where we can see these sedimentary rocks. We can see the different beds. So we have an alternance of beds depending on the season, the granulometry of the grain of the components of the rock, and whether there was water or not. So this would explain the changes in the colors. But as you can see, it is composed mainly of different types of layers, strata, stratified rocks. This is a good example for sediments. Here is an example for stratified stacked layers of volcanic rocks. So there are lava flows and ash beds that are layered on top of each other. And how are these formed? Well, the sedimentary layer is formed from deposits coming from the continents, as we've seen in lesson 1. And these sediments are going down, redeposited through several processes like erosion, wind, water, and they deposit originally as horizontal layers, horizontal beds before any deformation. When it comes to volcanic layering, well, it depends on the deposit on which it is deposited naturally on each side or each limb of the volcano. There would be a stratification layering, but it wouldn't be a horizontal because it would be set on the deposit that is already installed. This is an example of another kind of layering, which is within a mafic rock. So mafic rocks, as we've seen in lesson 2, are basically dark minerals forming the rocks. So here we have an alterance, what we call primary layering, which is not caused by any deformation or metamorphism. It's really natural. There is a layering between mafic and felsic rocks, and is formed by accumulations of crystals by sinking or buoyant rise, accumulating in specific subhorizontal layers of the magma chamber. If we go on to non-layered rocks now, so these are mainly within igneous rocks. Example would be a granite, which is formed in deep underground cooling, permitting crystallization, so nice eye-size crystals, so no layers are developed, and metamorphic rocks, which are extensive metamorphism and remelting no longer preserves the stratification, with few exceptions. Examples of non-stratified rocks on the field, so we can see here intrusive igneous rocks, here mainly granites, exposed by erosion, and you can see their bubbly, massive look with no bedding or layering. Here we have an example which is mainly non-stratified on the bottom, as you can see here, with like a massive look, and at the top we have the contrast with stratified bedded layers. To understand also the geologic principles for rock deformations, we have to go through some basic geological principles. So they were defined in 1669 by Nicolas Steno, and they were then elaborated by Scottish geologists James Houghton and Charles Lyell, which are really the basic of the geological principles. There are 3 laws that are used to resolve the relative age of rocks and the order in which they formed or as geological events. These basic principles are easily observed in geologic outcrops, and we'll be covering them between this lesson and the next lesson. And it's something that has to be observed when we have layered rocks or strata. And they are pretty logical and important for various scientific and technical applications beyond geology. So before going into these laws, this is just a simple way to express why we need to go through them. If we are on the field, before looking at rocks, we look on the ground and we see some traces of different tracks, and we're wondering who passed before who. So we have examples here of bear paws, bird, deer, dog, bobcat, human, and we have blood, and we just want to understand what happened here. Who ate who? As an example. So the same thing with geology, with the rocks. We want to know which ones arrived first, how they got deformed, and their events. So it's only a question of what is the order of superimposition. Sometimes it is not clear as they seem, and inferences can be made. So starting with these laws, the first one is called the law of original horizontality, which states that most sediments, as we talked since the first two lessons, sediments originally deposit in horizontal layers. So before any deformation, common sense, anything that falls on the ground deposits horizontally. So before any deformed layers, some deformation that can change these could be faulting, tectonic forces, and volcanic activity. Example here, the law of original horizontality. At the top, we see a previous deposit and the sediments which naturally deposit horizontally on top. So it would deposit as this example, and they would never deposit like this. This, we would know right away that the rocks from above would have been deformed. The second law is the law of superposition, meaning that in any undisturbed sequence of rocks deposited in layers, the youngest layer is on the top and the oldest on the bottom. If we go a little bit further, meaning that each layer being younger than the one beneath it, which makes sense, and each layer being older than the one above it. So here, an example with an undisturbed sequence of rocks, again, with no deformation, without even knowing their numeric ages, we would know logically that C deposited before B and B deposited before A, and so on. So the younger rocks overlie older sediments. The third law is the law of cross-cutting relationships. So this law states that a body of igneous rock, an intrusion, any fault or other geologic feature, like a dike, must be younger than any rock across which it cuts through. So whatever event cuts through another prior deposit has to be necessarily younger than what it cuts through. So if we have a visual of this, on the left, we can see an intrusion. So the intrusion will cut through the unit B. So we know the unit B was here before the intrusion cuts through. So the intrusion has to be younger than B. On the right, we have unit A, which is deposited, and we see this fall, which dislocates and displaces unit A. So we know that B, which is a fault, has deformed unit A, so, and is younger than unit A. So these are evidences that we can use to know their relative chronological age. Another thing we have to take into consideration also through our investigations is that consider the geological principles are the gaps. We often have gaps within rock layers, and these are mainly caused by erosional boundaries that are called unconformities. So we see them on the surface formation where there was interruption, so interruption in deposition or interruption for periods of time of pre-existing data, strata, followed by renewed deposition. So erosion are the main causes of unconformities. Keep in mind that unconformities can be complex, and if they take place in one location in geologic time, maybe somewhere else along the line, the sediments were preserved and they are not continuous. So an unconformity in one location may span about a time in another location. So a non-conformity is known to occur between sedimentary rocks and metamorphic rocks or igneous rocks. When the sedimentary rock lies above and was deposited on a pre-existing and eroded metamorphic or igneous rock. So to illustrate that, we see here at the bottom we have Precambrian metamorphic rocks with a contact that is not direct between the two. And on the top, we have a sandstone that deposited itself. So we can see that the contact between the two is not direct, and it's called a non-conformity. So we have the older rocks at the bottom and the younger rocks at the top. We have the angular unconformity. That type is easily recognized because of its angle, which is in the name. So it's an unconformity where horizontally parallel strata of sediments, rocks are deposited on tilted and eroded layers. And this will produce an angular discordance between the two. So this shows it well. So we have the prior sediments that are now subvertical. They have been folded. We have the contact here, and the contact with the new sediments which are horizontal causes an angular unconformity between the two. And we have the disconformity, the third one. Disconformity is an unconformity between parallel layers of sediment rocks, which represents a period of erosion or non-deposition. So it could be a hiatus in time and deposition of rocks too. So here, the disconformity between the two would be seen with things we could find in either units between the limestones here at the bottom and the sandstones at the top. The final one is called a conformable boundary, which is an arrangement where layers of sedimentary strata are parallel, but there is a little apparent erosion in the boundary between the two rocks there, and they resemble a simple bedding plane. So it's little evidence to support a significant passage of time occurred as a conformable boundary. So a conformable boundary is gradational contact, and that again can be seen wherever we can find to be able to date both units. So if we go on the field to go see these kinds of discordances or unconformities, we can see here at the bottom we have an igneous and metamorphic rocks and the sediments on the top. And we can see there is a line here that really contrasts between the two, which is not a gradational contact. And we can see there's a nonconformity between the two. If I come back here, we have 3 units that shows disconformities. So these are tagged with the different fossils found in time, and we can know that they are, even if they are between on top of each other, they are from different times, and there has been a hiatus or a break between them. And this one shows very well image of angular unconformity here, as we see the beds that were once horizontal that are now folded, and they cause an angular contact with the unit on top, which has horizontal beds. This one here is the conformable or gradational contact. So between the two, even if the two units have horizontal layers, there are evidences inside that show that they are not from the same time. There was a break between the two, and they are gradational. So how do unconformities form? They're mainly caused by relative changes in sea level over time. So wave erosions wears away materials exposed along coastlines. So it surfaces, it smooths out the surfaces. On scales of thousands to millions of years, the shorelines move across entire regions. The erosion strips away materials which exposed to waves and currents. New, younger material can be deposited on the scored surface. Shallow seas may flood and then withdraw repeatedly, and long-lasting transgressions can erode away entire mountain ranges with enough time. Here is the principle of the transgression. Transgression happens when there's a rise in sea level, so it creates a space underwater for sediments to be deposited. Any younger or new material is deposited on the scored surface. And this can be seen also with unconformities, different kinds of unconformities. The opposite will be called the regression, and that's when the sea level falls and the sediments are, during that time, the sediments are not deposited or eroded away. So how are the ages of rocks determined? So also it's important to understand before going into the rock deformations to know what happened first. So geochronology is the branch of earth sciences which is concerned with determining the age of earth materials and events through geological time. So geologists have many ways to determine the age of materials using relative dating and absolute dating methods. So we want to know several things when we're on the field. We want to determine the age of rocks, fossils. How do they figure out how long ago and in what order the geological processes or events took place? The geologists also want to know how often a volcano will erupt, how often earthquakes takes place. So there are several methods to determine that. The relative dating is used mainly in the field. So once we want to know in which order the events happen without necessarily knowing their absolute age or their absolute age number. So the relative dating involves the study of fossils and the correlation or comparison of fossils of similar ages, but from different regions when their age is known. And the microfossils derived from sediments and cores from wells help in the subsurface exploration of oil and gas. So using the three laws that I presented before, what we have to remember is that the law of original horizontality will dictate that the sedimentary layers were originally deposited as flat layers. So once we arrive on the field and we see flat layers, we know that they were not deformed. The law of superposition will dictate if a series of rock layers are exposed, which ones, so we know that the ones at the bottom will be the oldest and the one on top will be the youngest, unless there was some disturbation during the geological event. So in that case, we will also apply the cross-cutting relationships law, which dictates that the rocks will be older than the forces that later change them. So whatever cuts through, like a fault, whatever folds them, intrude into them, and any formation from volcano. So if we take this image, is a simple way to understand these relative aging. We have unit C, B, and A, D, and we have an event E, which is a fault. So if we see this, we see often walls like this along highways, and geologists will stand here and will look at these units and will say what happened here, what are the events of the sequence here. And if we take the law of horizontality, we see that C will be the oldest, and then B sedimented over, and then A. We see that C, B, and A are cross-cutted by D, so we know that D necessarily has to be the youngest between C, B, and A. But we also see that now that D has been dislocated and displaced along the fault plane. So we know that the fault is the youngest event in this image. And so we know that D and then E happened. And then the final one that we often forget is the erosion process that we still have to check along the line. And we see here that the erosion process has uncovered the dike. So if we take each step one by one from the law of original horizontality, we see that layer C deposited before layer B and deposited before layer, and B deposited before layer A, which is pretty logical here because there are no deformation. We see that feature D, which is typical of an intrusion dike, cuts through C, B, and A. And we see that the final feature here, E, which is the fault, broke through all the layers, and that the erosion exposed some of these features on the surface. So if we go in the field, this is a good example that shows these rocks which were deposited horizontally and were later folded. So the oldest rocks here are on the right, and the youngest rocks are on the mesa, or mesa here means the top, the table, the plateau on the left. Here is an example of using the law of original horizontality again. So we have a series of sedimentary layers and volcanic ash deposited here. And we can see along, if we look along the bedding of the strata, that, oops, if we follow along here, all of a sudden we lose it. It either went up or down. And we have these lines here. So these lines we know corresponds to our faults. And we see here, if we walk along the beds, we usually walk along the beds to see what happened, and oops, we see a block going up or down. So we know that these faults have to be younger than the deposition of the beds. So the law of cross-cutting relationships shows that the offset of the units, faulting, must have happened after they were deposited as layers. So it's questions of logical observations. Here again, we have a series of sedimentary layers which were deposited as horizontal before they were forced up. And these layers you can see that are now subvertical. And we can see that they were affected by a fault. So we can see that the fault is the youngest event in this area. Here we see bedding, which is subvertical. So we see that the fault is younger than the sedimentary rock formation on either side of the fault. And the age of the two rock formations on either side would have to be determined by some other means, like fossils. So if we are in the field and we're able to recognize some of these fossils, we would be able to determine an age. If not, it would be ongoing work on the lab, on the samples. Here is an example of cross-cutting relationships. So we have the dark basalt here in this dike, which is younger than the pinkish volcanic rocks on either side. So anything that is being cross-cutted by is always older than the element that cuts through that element. So the exact age of the volcanic rocks would have to be determined in other means, but we can at least put a relative age on the field on these rocks. So we're going to start to go through the structural deformation, the physical structural deformation types. We're going to start with the folds. So what are folds? They occur in one layer or stack of originally flat planar surfaces and are bent or curved as a result of permanent deformation. So a fold is the bending or warping of stratified rocks, in simple terms. So anything that is not horizontal but has, like now, a zigzag effect on it, we know that it has been folded. So there's many scales of fold. We can have microfolds, tiny microfolds in hand samples. They can be seen by a microscope, and they can go up to larger scales that can be seen along the roads, or larger scale even through mountain ranges. So the elements, the main elements that form a fold are called hinge. So the hinge line here. The hinge line is the highest point on the stratum. So if you start at the limit of a stratum and you go on and you find the top highest point on the stratum of the curvature, you know that the hinge line passes there, and we can draw perpendicular to that line what we call the axial plane, which is along the hinge zone. Both sides are called the limbs. And that curvature point is also known as a crest. So the inflection point is the area on the limbs where the curvature changes, which is the hinge line. And what we have here is to show the difference between symmetrical fold and asymmetrical fold. So symmetrical fold simply means that on both sides, both limbs have the same equivalent dips. Asymmetrical fold means that the actual plane is tilted, meaning that one side, one limb would have different dip than the other side. On the field, this is a good example of an asymmetrical fold. So if we start on the limit here and we go along the strata until the toppest or maximum curvature, we're able to draw this line, which is the axis of the plane, and then we're able to define the left and right limb. We see that between the left and the right limb, the dips are different, so we know that it is an asymmetrical fold. The fold types, I'm gonna go over a couple of simple fold types. Main one is called an anticline, as seen here, and it is where the concave side faces down. So, and it's also easy to remember, anticline has an arch-like, so A for anticline shape, where the oldest beds are in the core and the younger beds are within the outer limbs. The convex side is up, in which the hinge or the crest is the location where the curvature is the greatest, and the limbs are the sides of the fold that dip away from the hinge. So the hinge being this line here, the limbs we can see are going away from that line. If we had an anticline within a nice stratified rock, this would be the reflection of the rocks if we did a cross section over it versus what we see on the surface. And this cross-cutting would help us place where the axial plane is and define the symmetry of the fold. If we had an overturned anticline, same thing, same process. The only thing here is that the axial plane would be like this, and we can see that the limbs dip where one would be overturned versus the other. So it's basically it's a flipped over and made dip in the same direction on both sides of the axial plane. A syncline is a complete opposite of an anticline, and as you can see, has a U shape. So having the U shape, we know that the center is the youngest, and the U-like shape falls in which the limbs dip toward the hinge, as we can see here, and the oldest rocks of the strata are within the outer limbs. So, and they are usually seen within the flank sides of anticlines. On the field, what we do is we just follow the strata. So here, if we follow strata, we can see that we're going down into a U shape. So we know already that this is a syncline. Going down the curvature, the maximum curvature is around here. So we know how to draw the axis plane of the fold. If we move over, then we go towards an A shape. So we know that we're moving around to an anticline, with the maximum point of curvature being here, so we can draw the axis plane. And if we go on here, we see that there is a break, and we see that these strata beds are displaced or dislocated along this line, so we are able to define a fault as it was drawn here by the geologist sketch. So sketches are very important, as we will see in the next lesson. And then we can go on to see the continuity of this fold. So here what I did is I placed an anticline and a syncline sequence before any other type of deformation. So structural deformations can become very complex one after the other. Here at the top is a simple anticline, syncline formation, and then a little complexity will come over, which is a syncline, anticline, which has been folded. So there's part of the anticline that has been displaced, and we can see also a difference in the dip. Another example here of a sequence. So if we always start from one limit of the rocks or panel that we see. So if we go up here, maximum curvature is here, and we're going down, we are seeing that we're doing an A shape. So this has to be an anticline. This has to be its axial plane, and we can see that it is an asymmetrical anticline. If we continue over, we see that we're doing a U shape. Maximum overture is around here, so we can place the syncline axis here, and so on. If we're looking at these type of folds in the field, they're not always well equal. So that's an example I want to show here. So we're starting here with a nice anticline, symmetrical anticline, going down to a symmetrical syncline, and oops, we're going over to an asymmetrical fold here. So we can see that one side of the limb, the other side of the limb on the fold axis are not dipping the same way. And then we move on into what we call an overturned fold, overturned syncline. So here the limb is overturned along the axis plane line and falling back down here. So if we're looking here at these examples on the field, so here we have a nice symmetrical anticline, a nice symmetrical syncline, and an overturned here anticline. So overturned fold has its axial plane inclined to such an extent that the strata on the limb are overturned, as it says in the word. Here is an example of ridge lines of sedimentary rocks stand out with plunging and anticlines and synclines folds as seen by aerial views. So that's a mega scale folds. Other types of folds would be domes and basins. So domes and basins are the opposite one of the other. The domes is a structure that plunges in all directions to form a circular or elongated structure in the form of a mountain. So the top would be here, would be the oldest strata, and the beds around would go dip away from the center. The basin is the opposite. The youngest strata is in the center, and if you're going towards the outer portion of the basin, the walls of the basin would all dip within the center, so completely opposite. If we have the field example, so here is a circular dome. As we can see, the oldest part is here in the center, and the beds are dipping away from the center, so away from the dome's core. Here is a geological basin, so the opposite of a dome, and usually fills in with water and usually fills in as a lake. And these are usually used or searched for major oil and gas reservoirs. Other types of subfolds that can be found along either anticlines and synclines are what we call subfolds Z, M, or S. So if we're looking here at an anticline, we know that the Z folds are on the left limb, as we can see here. M folds are always in the hinge zone, forming M forms. And finally, the S folds are on the right limb, forming S-shaped folds. What we'll see later on is also that once these little beds are microfolded, that the elements within these areas, either in the hinge or the limbs, are also deformed along these either Z, M, or S folds. So if we look here at the succession between an anticline and a syncline, we see the dispersal of these Z folds, M folds, S folds. And what we have to understand is that between an anticline and a syncline would be the opposite. So the Z folds on an anticline would be on the right, the S folds on a syncline would be on the left, and the hinge zone will always remain with M folds for both. So on the field here, we can see these typical faults. As we can see here, this one is for the M faults between either anticline or synclines, forming an M-shaped fold. And then we have here the nice Z fold and the S fold within either if we're on the anticline or a syncline. Now we're moving on to the fracture types. So fracture types, they're known as fracture. A fault is called a fault only if we can find a displacement along this fracture. So if we have movements that may occur, if we have rapid movements, it's an earthquake. If we have slow movements, it's a creeps or slow downslope movements. And faults are usually associated also with folds. When we have a fault for a fracture to be known as a fault, it has to show a motion between each side of the blocks along that movement. So these are known as block A or block B. So we have terms calling them either the hanging wall or the footwall. So the relative motion between each blocks along a fault are always described based on the hanging wall or the footwall. So the hanging wall is the block or the side of the rocks that on the upper side of an inclined plane. So it's the side you could hang from without your feet touching the ground. So that's called a hanging wall. And the footwall would be the side where you could stand on and move upwards. So that would be the footwall. So these are important to know because that's how we recognize between several types of faults. The one I will present today are the normal fault, reverse fault, the strike slips, the thrust fault, and the oblique slip fault. So if we start with the first, like I said, to describe these faults, we really need to know the movement, the relative motion of these faults, which is described between the hanging wall and the footwall. So if we start with the normal fault, as seen here, is that the hanging wall, the one where we can hang in from, has went down, and the footwall, the one we can climb on, has went up. Also, the surface here of the slide or the slip, the dip has to be between 45 and 90 degrees. And these are often associated with on the field as escarpment of slumps. On the field, example of these. So we can see here, and this again is the relative observations that we can see through the layering or the strata. So if we move here along the strata and suddenly we see that this strata has moved on that way, so we know that along this line there has been some dislocation and displacement. So whatever went down is the hanging wall, whatever went up is the footwall. So this is a good example on the field of a normal fault. Another good example here would be with simple horizontal planes that have not been folded. The example before were from folded planes. So the non-folded here strata, if we move along the strata here, we see that the block here is not continuous. And then we go look on each side and oops, it's here. So we know that each part, which one has went down and which one has went up, and we can define here again a normal fault. Another example would be here, and on the field what we usually do is we also measure the distance of displacement between two known blocks that would have been continued before being faulted. And that would give us the differences between a major and a minor fault. If we move on to reverse faults, which is shown here, it's the complete opposite of a normal fault. So the hanging wall went up and the footwall went down. The surface slip here is the dip is the same as a normal fault, would be between 45 and 90 degrees. So if we go in the field, we always look at what went on. So we see the bed here, we move along, and oops, we see that there's something that has displaced it. So where did it go? We can see that this went up. So this would be the hanging wall going up and the foot wall going down. So we know that we have a reverse fault. So a strike and slip fault is contrary to the normal and the reverse fault. It is a sideways, so a horizontal displacement. There are no displacement along the vertical line. So that's an easy way to remember. And the strike slip fault, we have an additional tag that we can add to it is, was there a right movement or dextral, or was there a left movement or sinistral? So along the horizontal line here. So if we position ourselves along here and we look facing perpendicular to the displacement, did the block go to the right? If it went to the right, it is a dextral movement. If we place ourselves here, looking perpendicular to the block, if the block went left, it is a sinistral movement. So the best example in the world for strike and slip fault is the San Andreas fault. As we see here, along the line of the fault, there are no movements in the vertical way. So on either side, the elevations are the same. The movements are along the horizontal plane here. The next one is the thrust fault. The thrust fault are hanging walls appear to have moved upward relative to the foot wall, and the big difference between the reverse and the normal fault are their dip angles here along the side. They have to be 45 degrees or less. So that's what we call also sub-flat faults. So the horizontal compression or rotational shear displacements is very steep. So this is a good example of a thrust fault here. As we can see, the angle is 45 degrees or less along the line. And then we have the deposition of younger rocks on top. The final one that I will present is the oblique slip fault. So this has both displacements. It has displacement along the horizontal line and it has displacement along the vertical line. So along the horizontal line is the strike slip, it gives us the strike, and along the vertical line, it will give us the dip of the slip. So it combines the strike slip motion with significant normal reverse or thrust offset. When we have a group of faults, we have different types of group of faults that we call fault zones. One that is well known is the horsts and graben. So they're result of tensional forces which act up over a region and can produce normal faults that result in landforms known as horsts and grabens. So what's to remember here? The graben is the block that goes down relative to the crust, and the graben is surrounded by two horsts. The horsts are the blocks that went up. So if we look at an image here, we see a graben which is surrounded by two horsts. We see that the grabens went down and that the horsts went up. And they're formed with what we call a tensional force environment, so they are pulled apart. Best example on the field would be when you see a series of mountain ranges crests versus mountain ranges. Between two mountain ranges crests, you see a valley. Well, the valley is the graben block that went down, and the horse would be the mountain crest ridges that went up. So if we cut through here, we could either have just movements of these blocks and the layering of the beds stay horizontal, but we can also have the layering of the beds on the bottom that were displaced and also folded. So here is a stretch by tensional forces that we have a series of normal faults. Again, here on the field, it's very evident. If we move on to on the field, grabens are also known as rift valleys. So between any rift, there's a valley. So there are the grabens, and whatever blocks were raised are the horsts. Fault zones are also known, can also be known and become very complex, and we call them fault networks. So they can be small, they can be large, it can be seen either through a microscope, hand sample, or very extended on the field. So these are different kinds of primary, secondary, and tertiary interlinking faults, and they change from one kind of fault in one location to another, and they split, they bifurcate, they emerge, and they can pinch out. Pinch out meaning that over distances we lose them, and there's no more faulting. So fractures, fault networks can be very complex. This is a good example that shows all kinds of fault zones within that fault network. So what we do once we're on the field here is first we try to take out on that wall the major faults. So we just draw the major faults. What we'll see in the next lesson, when we draw these, anything from the field, when we have continuous line, we know we are sure of it. When we have a dashed line, is that we are not sure of 100% evidence, but we still draw it. So we can see here the major faults were drawn. Then we have the major primary faults were drawn. Then we have secondary faults which bifurcate or splays from major faults. And then we have sub-splays from the splays that form, and so on. So we have different orientations. We have different importance of the fault. We have major faults, minor faults, micro faults, and so on. So it can become very complex. If we move away from a fault, we also see on the field evidences of showing us if we are close or not from a fault. So here, if we are within the fault plane, is we are really within the fault. The next texture we see, what we call fault gouge, is within the fault plane, is that nothing is recognizable. Everything is like a clay, everything is destroyed. We have no more evidence of nothing of the original rock. Then if we move a little bit farther, we have a fault breakout on each side. We have a recognizable rock, but very fragmented. So a lot of fragments within a thinner matrix. If we move a little bit away from that rock is not yet fragmented, but we can see some fractures in it, some foliation. Foliation meaning that there are some preferential orientations of the elements within the rock that has undergone with the structural deformation. If we move a little bit farther, we have a non-foliated rock. That means we have some fractures, but the elements inside are not along a preferential plan. And then farther away, we have small fractures, and farther away, we have the non-deformed rocks. So these evidence also shows us how far away we are from a main fault. The next thing to cover to understand well the structural deformation is the response to stress and strain. Rock deformation is also based on the different kinds of responses we have for stress and strain applied on them. So elastic deformation is small differential stresses, and they are less than the yield strength. So the rock deforms, we have to understand that it deforms like a spring. So it slightly changes the shape in response to the stress, but the deformation is not permanent. And if the stress could be reversed, the rock will return to its original shape. The brittle deformation is all of a sudden the rock behaves in a brittle fashion. Brittle meaning that it will break. So that means that the stress applied on it is greater and the rock will fracture. So part of the rock that didn't break springs back, but the elastic rebound, a good example for that would be the elastic rebound that causes earthquakes. But you have to understand that in brittle deformation, it breaks. In ductile deformation, that happens in deeper areas, so between 10 and 20 kilometers. It is nearly impossible to produce a fracture here because the high temperature makes the rocks softer, less brittle, and more malleable. So it's like a plastic deformation. That means it will change in shape, and the stress is stronger, and it would yield like flowing textures on it, and we'll see examples of that. So just to explain the differences here, we have the types of stresses the rock can be affected with, and the same example of these stresses if we would be holding in our hand a stick, a wooden stick. So the original position here, so nothing happens. We're starting to try to fold the stick. So trying to fold the stick, we see a buildup of strain, trying to fold here, and that's what we have here, the building up of the strain. And this building up of strain, we see it here with the apparition of the fault, and all of a sudden, whoops, the stick would break. So holding it up, we would create what we call slippage, and that would causes the waves, and the waves would cause here, as you can see, the earthquakes. And finally, the strain is that the strain has been released, and there's a strain released here, and it would stop here, the deformation. So it's what we call the elastic rebound and earthquake concepts. So what you have to understand basically between stress and strain is that once you move from with depth, the thing to understand is that structure changes with depth. So once you're at the top, surface, subsurface, the deformation is fracture-like, brittle-like, and until what we call a deformation point, it's the rupture point, which is the X here, which is the difference between the brittle plastic ductile deformation and the elastic deformation. So if we see this in image, this one is a great image to understand all this, is that if you are in the upper subsurface areas, which is here, first you are here, there is no deformation, the beds are deposited horizontally. Then if you are in the upper subsurface areas, the kind of deformation you can have are the faults and fractures, which we can see here. Once we go into the intermediate depths between 10 and 25 kilometers, the reflection of the units are starting to be seen, as seen here as an anticline fault. Deflection and the type of faults will develop. Once you go into the lower portions, greater than 20 kilometers, we have flattening and sliding of these units on top of each other. And then to major depths, you would see the flowing events, the flowing texture that would form within the rocks. So all the elements within each rock strata will be flowing or stretched out to follow these bending of the rock. So the depth formation, the deeper the rocks, will be subject to higher pressure and temperatures. The total time of a rock undergoing the stress, the rocks behaves very differently at depth than at the surface, and the rocks deform in a more fragile, brittle manner near the top, and a more plastic manner here as seen at depths. This is also shown here. So from the top, undeformed blocks, brittle, and then it's a ductile deformation, and ductile deformation, the elements inside also follow that deformation and changes orientation. So these responses are also different between the depth, as we just discussed, but also between their differential stress environment where they were into compression, so the blocks going towards each other, tension, the blocks going away from each other, and the shear, the blocks sliding on each other. So that's the major at shallow depths, how they would react, and at deeper depths, how they would get deformed. So we will see that within rocks. So these kinds of changes, so within the brittle or upper parts, and if you're into compression environment, you will have a reverse fault here, tension environment, a normal fault, and a shearing, you'd have here an example of a reverse fault. If we're into deeper parts, we have within the ductile environments, we have here for compression, an example of a fold. Within tension, an example of boudin or boudinage. And the final one here, within the shear, we have the ductile shear zone. This image represents very well the flowing within the elements of a rock. What happens within these elements? Again, these changes are really based with depth, with the levels of depth. So in surface, subsurface area, more brittle, we have the faults and what happens to these elements inside. And then the types of folding that happens, the texture, schistosity texture, the inclined similar folds, overturned tight folds, and the final metamorphic folds, which transforms the elements within each bed to follow the compression and strain environments. Example here of a boudinage, so between a brittle and a ductile plastic, how the elements will react. Brittle, they will break angularly, and the intermediate depths, they would be between a subangular, and the ductile, you see, they would be molded or malleable and would form boudin, rounded boudin edges. And these are the same examples, but within shear, so shear environment and shear symmetric shearing and asymmetric shearing. So we will show how the elements would react. So these are well known and well seen on the field. So the faults versus shear zones, so faults being again between the upper and intermediate levels, and the shears being between the lower and infrastructure levels. And these, we really need to understand that the faults are the brittle parts, and they will break, and they will not reorient things here, semi-reorient things. Once you go to shearing, the elements inside will be reoriented along the strains and compression on the rocks. So these are all kinds of structural level elements that we use on the field to what we call the kinematic indicators. Kinematic indicators will show us how these were moved, deformed, broken, rearranged, and so on. So we have porphyroclast systems here, as we can see. We have brittle deformation zones, shear zones, how things react in sides, the folds, and finally the domes, diapirs, and plutons. So simple example here of anticline moving on to a syncline, how these elements inside each beds would react. So the ones in orange are the ones that are not deformed, and the ones in blue are the ones that would show inner deformations following the constraints. So the elements naturally respond to these strains to follow these constraints. Example here would be the crenellation within metamorphic rocks deformation. So the primary structures are reoriented during tectonic events. So that's really another physical change within the rocks. So the new planar structures may form by transposition or by formation, calling what we call the foliation. So everything inside is being foliated and reoriented along a preferential plane. Best example here on the field, so we can understand. So if we do a sketch of what's going on here, is we understand how these elements along the beds are responding to these strains and constraints. Now, if we move on to the geochemical deformations, alterations, geochemical deformations, contrary to the physical deformation, is that it involves a breakdown of rock by chemical means, so either decomposition, decay, or dissolution. So the weathering and erosion are continuous processes in the surface environments, and they're mainly done or undergone by water, which is the universal solvent. So it's also done by changes in air pressure, and you have to understand that it is really chemical variation within the rock. So the water is the most important one. So what does it cause? It will cause some dissolution and some leaching. Dissolution is the simple act of dissolving or being dissolved. So moving soluble components of materials into solutions will break down, the minerals will break down into insoluble and insoluble components. Leaching is the process of which dissolving and removing the soluble constituents of soil or rock near the land surface. So gravity water flowing carries dissolved materials, and this would add to the saltiness of the oceans or deposited as salts. So in everyday life, kind of geochemical weathering is the process of making tea or coffee is a weathering process. If you pour hot water into coffee grounds or tea bag, either one of them will dissolve and leach soluble components, not altering the insoluble components. So it's present in our everyday life. Before having the geochemical deformation, it is usually after what we call the mechanical weathering. Mechanical weathering is what we just covered, is anything that mechanically will transform a rock, so physically will transform a rock from anything that we just saw, mainly fractures, joints, and faults. So once these will cause some weaknesses in the rocks, they will also cause openings, canals where fluids can circulate. Once the fluid can circulate, water, CO2, any organic acids can cause any chemical weathering along these borders, and they will change the rock composition. So water is the most important agent for weathering. So they will cause along the fractures of the bedrock a change in chemical composition. The mechanical processes can also be caused by difference in temperatures, heating and cooling, and freezing and thawing. So these chemical weathering can be broken down into 4 different chemical reactions. You have the hydrolysis, chemical breakdown of a compound reacting to water. Hydration is the action of combining water to any other molecule. Oxidation is the process of combining elements with oxygen ions. Best example, mineral exposed can undergo oxidation. And the carbonation is the saturation with carbon dioxide, example, soda water. So what does these alterations do to minerals? If we take examples, minerals forming under high temperatures or high pressures may not be stable. So if we take the example of quartz, what happens to the quartz with geochemical deformation? As we've seen in lesson 2, quartz is a common felsic rock-forming mineral. Felsic meaning light colored mineral, and it is one of the most resistant to weathering process. So what happens to quartz? It will break down, but it will break down physically, but not chemically. So it will break down in surface environments, probably down into sand grains. What happens to feldspar? Feldspar, common mafic mineral, often included with sodium, calcium, potassium, and iron. These will break down physically and chemically. What happens to feldspar? Feldspar, mica, and mafic silicate will break down into what we call clay minerals, and iron that does not dissolve will hydrate or oxidize and essentially become brown colored minerals in the soil known as limonite and hematite. So these will react chemically to elements which will be dissolved in water, and they will also react to oxygen and carbon dioxide. So one of the best example, even if we have rocks here on the background, is the old car that we see here in front, which has been oxidized. So the rust has caused a chemical breakdown. So it's the same principle that would break down the rocks. So the main minerals that we saw in lesson 1, this is how they would react to insoluble and soluble contents. So the quartz, the mafic minerals, the feldspar, gypsum, calcite, what would happen to them? And we'll see that in detail in another lesson coming up. Just an example between two types of rock. If we take the felsic rock, the example of a granite, what happens to it geochemically after mechanical weathering? Both water and gases slowly chemically alter the minerals. So quartz will remain quartz, right? But it will be broken down to gravel, sand, and silt size. The feldspar and the micas will break down to become clays. The mafic minerals will break down into clays and iron oxide and constitute the residues known as hematite and limonite. And the soluble components will dissolve and carry away by groundwater or surface waters. They will eventually contribute to salts and seawater. By contrast, within intermediate to mafic igneous rocks, the example would be a basalt. After mechanical weathering, these volcanic rocks being dominated by fine-grained mafic minerals and feldspar, they will probably all break down to become clays. The sediments deposited along the streams and the valleys and the sediments deposited offshore of volcanic regions are generally dominated by the mud. And the big difference here between the basalt and the porous granite is also, as we've seen in the last lesson, is the crystal grain size also that causes it to break down to clays. So the effects of physical and chemical conditions on weathering is based on these factors, on the particle size, on the oxidation reduction effects, on the acid base versus base effects, and the color. So these are the main ones. The factors that influence weathering can be resumed here between the moisture present, the surface temperature, the mineral makeup, the particle size, and the time. Time is also one of the big events for geochemical deformation. It can take time, but it will happen through time. So this is the best example on the field that would resume what happens with the mechanical. What you see here are the mechanical alterations, so all the fractures happening here. And along these fractures, how the borders of the rock has been geochemically or chemically altered with the circulation of any fluids, mainly water, that would have affected these rocks. So the parts that are away from the fractures are less altered. Now we're going to finish with the metamorphic processes. So the metamorphic processes are also based on any chemical changes within the rocks. And they are mainly happening within rocks which are in deeper environments. And they are caused mainly by those deeper compaction forces and strains applied to the rocks. So the pressure and temperature increases to the point that the mineral recrystallization, I'm going to go slow, will eventually take place. So Conditions that are right for producing are metamorphic minerals and rock textures. So these are the different environments where these metamorphic processes take place. We have different facies, metamorphic facies, and this is where they are either on the continent or the oceanic crust, and their depth. If we take them one by one, they have been divided into green schist, blue schist, and fabulite, ecologic, and granulite. And this is the difference between their temperatures and pressures environments. So if we take one by one an example of rock, the green schist is the one that is between low temperature and moderate pressure. Green schist facies is one of the most seen on the field in the Abitibi area and the James Bay area. We have the blue schist. Blue schist is lower temperature but higher pressures, versus if we go back, green schist is low temperature but moderate pressure, and that's the big difference between the two. The aphabolite is high temperature and moderate pressure. The ecologic is high temperature and highest pressure, so they're both very high. And the granulate is highest with the highest temperature and the high pressure. So once we have these metamorphic processes inside, what we see is that the original rock, before being transformed metamorphically, the elements inside did not have a preferential orientation versus a rock that has been affected metamorphically. We can see that the elements inside have a preferential orientation now that is known as foliation, so foliated rock. So foliation forms from the recrystallization and realignments of minerals into bands perpendicular to the force directed to it. So it's mainly a rock texture deformation. These examples would show a protolite, which is the original rock, undergoing low-grade metamorphism versus high-grade metamorphism, how it will react. So the shale here would be transformed into slate, which be transformed into a schist, and finally into a gneiss. So it's the elements inside that change metamorphically. So it's the rock textures that change. Example with rocks, here with the foliation, it's a simple linear platy structures showing clear preferred orientation of the new mineral. So the elongate amphiboles are platy clays that we see. The minerals tend to align parallel under pressure. Here we see an example of crenulation. So cleavage fabric is formed in metamorphic rocks that experience two or more changes in stress direction. So it's superimposed foliations on it. The cleavage here is the capacity of a rock to split along certain parallel surfaces as seen here, and known as bedding planes. The slaty cleavage is formed by the reorientation and the alignment here of clay and mica minerals in fine-grained sedimentary rocks, so high confining pressures of slate. The schistosity here, which is the type of rock formations that characterizes schists, parallel arrangements of coarse-grained platy minerals. So the micas are the biotite and muscovite, and the chlorite and talc. And we have the gneissic rock texture here, which is a foliation which is coarsely grained minerals. Crystals were segregated into discontinuous bands. Each band is dominated by one or two minerals, so it makes it like a stripped-like appearance. We have a migmatite. Migmatite is irregular bands, as you can see here, of typical gneisses and schists with igneous character through partial melting. So it contains many smaller light-colored bands of igneous rock cutting through dark foliated schists and gneiss. The melonitic is a fine-grained, typically banded rocks, which is grinding, shearing, or crushing of other rocks. And we can see inside some of the nice porphyroclastic cinematic evidences here. And here we have the brecciated texture. Brecciated fracture is a rock that contains angular fragments within a cemented, which are cemented together within a fine-grained matrix. So the fragments can be millimetric to a couple of meters. So we're going to move now to the videos to resume what we just saw. So we're going to resume, we're going to go back and do a little summary of what are the rock deformation causes and types.
Did you know that rocks experience stress? While not the same kind of stress that you might experience on a bad day, the stress rocks are subjected to still has quite an impact. Stress causes rocks to deform, meaning the rocks change size or shape. There are different kinds of stress that rocks experience, and these determine how the rocks deform. Tensional stress is when rock is stretched apart. This is similar to pulling on a string from both ends after the string has already been fully extended. Compressional stress is when rock is pressed together. Here, rocks are squeezed together like a car caught in the middle of a long pileup on the highway. Shear stress is when rock slips in a horizontal direction. With shear stress, the rock is being pulled in opposite directions, but on different ends. To understand this, try putting your palms together and then rubbing them back and forth. Now imagine that there's a rock in the middle, and you can see how one end goes forward while the other end gets pulled backward. As rocks are stressed, they go through stages of deformation. At first, the rock is strained enough that its shape or size may change, but the change is reversible. This is the first stage, called elastic deformation. Think of this elastic change like the elastic in your waistband. If you pull it and then let it go, the stretch is reversible because it can go back to its original shape. Rocks may also become so deformed that the change is not reversible, which we call ductile deformation. Ductile means that something can be changed into a new shape, but once this happens, it stays that way. This is like the copper wiring in your house. Copper is ductile, meaning you can stretch it into long, thin wires. However, once you've made this change, you can't unstretch it, and the same is true for rocks in this stage of deformation. Finally, if rocks are stressed enough, they fracture, which is when the change is irreversible and the rock breaks. If you fall down hard enough, you may fracture a bone in your body, and rocks experience the same thing when the stress is great enough. Some people handle stress better than others, and rocks are the same way. So, just like there are various types of rock stress, there are also different responses to the stress for different types of rock material. The ability of a rock to handle stress depends on its elasticity, or the flexibility of the rock. You might be surprised to learn that rocks are flexible. Under the right conditions, they can flow very slowly. This movement is similar to silly putty. Push on silly putty very hard and it feels like a solid, but pull it apart and it moves like a liquid. Rocks are not quite as fluid as silly putty, but sometimes they can act similarly. Do you remember from before that ductile materials like copper can be reshaped? The same is true for rocks. Ductile rock is rock that flows in response to stress. These rocks are more flexible than not. Things like clay and mica minerals are ductile materials, which you've experienced if you've ever played with clay to mold it into different shapes. Alternately, there is also brittle rock, which breaks or fractures in response to stress. This type of rock is less flexible and therefore cracks under pressure more easily than ductile rock. Examples of this type of material are quartz and feldspar minerals, which would break very easily if you drop them on the ground. The material of the rock is just one factor in how it deforms. Temperature also plays a role because at high temperatures, material can flow more easily, so it's more ductile. The opposite is true for low temperatures, so materials are more brittle and break more easily. Water is also important, and the less water present in a rock, the more brittle it is. Let's use clay as an example again. Wet clay is easy to mold and shape because it still has a lot of water in it. But when you bake it in the kiln, this removes the water and you can no longer change its shape without breaking it apart. Cement is the same way. When you add water, you can pour and shape the material almost any way you like. But as soon as it dries, you have to break it apart with a jackhammer to get it to change at all. We often think of rock as hard, brittle material. Throw a rock hard enough on the ground and it will likely break into pieces. But under the right conditions, rock can actually flow in a way that keeps it from breaking. When rock deforms in such a way that it bends instead of breaking, we call this a fold. Folds come from pressure on rocks that occur over very long periods of time, think millions of years. So instead of a quick action like throwing the rock on the ground, it's more like standing on it for millions of years until the pressure is finally enough that it changes shape. Folds are created in rock when they experience compressional stress. This is when the rock is being pushed inward from both sides. This is like if you put a spring between your hands and push them together. As you push, you're compressing the spring, and rock can be compressed in the same way over long periods of time. There are different types of folds created by compressional stress depending on which way the rock bends. An anticline is a fold that arches up as both sides of the rock are pushed inward. You can remember that the anticline creates this type of fold because the arch looks like an A for anticline. A syncline is a fold that sinks down as both sides of the rock are pushed inward. You can remember that a syncline creates this type of fold because the fold sinks downward, which sounds like syncline. A monocline is a fold where the rock layers form an S shape as the sides of the rock are compressed. You can remember this type of fold because all the layers of rock are still horizontal, going in one direction instead of bending vertically upward or downward like anticlines and synclines. And since mono means one, monoclines are layers in only one direction. We also have domes, which are like anticlines, but instead of an arch, the fold is in a dome shape, like an inverted bowl. Similarly, there are also basins, which are like synclines, but again, instead of a sinking arch, the fold is in a shape of a bowl, sinking down into the ground. Not only do folds come in different shapes, but they also form at different angles. Symmetrical folds are folds with the same angle. This makes sense, since symmetry means the same on both sides. We can also have the reverse of symmetrical, which occur in asymmetrical folds, or folds with different angles. Isoclinal folds are similar to symmetrical folds, but these folds both have the same angle and are parallel to each other. Iso means the same, symmetrical, and cline means angle, so this name literally means same angle. So isoclinal folds are both symmetrical and aligned in a parallel fashion. Overturned folds occur when the folding is so intense that the fold appears to have turned over on itself. Similarly, we can have recumbent folds, which are even more extreme than overturned folds. These are folds that are nearly horizontal. Recumbent means lying down, so you could think of this fold as lying down sideways. Finally, we have chevron folds, which are folds in a zigzag pattern. The angles of the folds are shaped like chevrons, and instead of slowly curving, the edges are sharp and straight.
You have probably noticed that no two rocks look exactly the same. Some look like they have been carved by a sculptor, some look like they have been painted red, and others have been hollowed out to form caves. One of the reasons rocks look so varied in their appearance is because they are subjected to chemical weathering, which is the process by which rocks are broken down by chemical reactions. In this lesson, you will learn about the different types of chemical weathering and how exposure to things such as water, oxygen, carbon dioxide, and acids can alter the minerals found in rocks. Now, we mentioned that chemical weathering is a way in which rocks get broken down. But it is important to emphasize that because there is an actual chemical change taking place, rocks are not just crumbled into smaller rocks. They are actually being chemically altered. In other words, after chemical weathering, we end up with a different substance than the one we started with. There are different types of chemical weathering. Let's start with a discussion of hydrolysis, which is the chemical breakdown of a substance when combined with water. You can recall this term by remembering that the prefix hydro means water and the suffix lysis means to break down. With chemical weathering of rock, we see a chemical reaction happening between the minerals found in the rock and rainwater. The most common example of hydrolysis is feldspar, which can be found in granite changing to clay. When it rains, water seeps down into the ground and comes in contact with granite rocks. The feldspar crystals within the granite react with the water and are chemically altered to form clay minerals, which weaken the rock. An easy way to remember hydrolysis is to think of it as the same process you go through each morning when you make a cup of coffee. When the water you add to your coffee maker heats up, it filters down through the coffee grains. The water chemically reacts with the coffee grains, giving you a chemically different substance called coffee. Another type of chemical weathering is oxidation. Oxidation is a reaction of a substance with oxygen. You are probably familiar with oxidation because it is the process that causes rust. So just like your car turns to rust through oxidation, rocks can get rusty if they contain iron. You may have noticed that rusted metal on your car is somewhat fragile. You could even poke your finger through a rust patch if it's big enough. This is because when iron reacts with oxygen, it forms iron oxide, which is not very strong. So when a rock gets oxidized, it is weakened and crumbles easily, allowing the rock to break down. Iron oxide is a kind of brownish red in color, and this explains why some rocks look red. Carbonation is another type of chemical weathering. Carbonation is the mixing of water with carbon dioxide to make carbonic acid. This type of weathering is important in the formation of caves. Dissolved carbon dioxide in rainwater or in moist air forms carbonic acid, and this acid reacts with minerals in rocks. The mineral calcite, which is common in limestone, is particularly vulnerable to carbonation. This mineral dissolves in the carbonic acid and gets washed away. This can hollow out the rock and leave behind a cave. Another type of chemical weathering involves lichens. Lichens are a combination of fungi and algae and grow on rocks and produce acids that break down the minerals within the rocks. When water mixes with the lichens, they produce a weak acid. This is a very slow process because lichens are slow growing and the acid they produce is very weak. However, this is a common type of chemical weathering near rivers and streams. So we see that lichens break down rock by producing acid, and we see a similar phenomenon with acid rain. The EPA defines acid rain as rain that has been made acidic by certain pollutants in the air. When pollutants such as sulfur dioxide, carbon dioxide, and nitrogen oxide are produced by activities such as burning fossil fuels, these pollutants are put into the air where they mix with moisture. This process produces acids such as sulfuric acid, carbonic acid, and nitric acid, which falls to the ground as acid rain and chemically weathers rocks.
Okay, so do you have any questions? Is there any questions? No, no questions
for today. Once again,
Thank you very much.
Yeah, and just one more thing. Once again, for the people that might watch, just hang out there for a minute.
Yeah.
That might catch this after the replay. If you have any questions, feel free to email them at info@iddpnql.ca. We'll make sure they reach Francine, and we'll try to provide you guys with an answer. Once again, thanks for tagging along with us. We'll see you on March 19th for the 4th installment. Take care.
Bye-bye.